Math 287, Cuesta College. I'm Joe Vasta, and we are going to cover section 10.1a. I actually break them up into two parts. I think your book should have done it, but it didn't. And you might see when I'm done why I did it this way. This is called the Laplace transform. This might be the most important thing that some of you engineers will see in this whole class. The Laplace transform is something that is used a lot. And if you don't believe me, go up to an engineer friend or family member and say, we're learning Laplace transforms in our math class. They're not important, they're stupid, and watch what happens. Okay, see how mad they get. The Laplace transform is essential to a lot of problem solving. So we have a second order differential equation, and it's linear, and you have your driving function. The question is, what if your driving function is intermittent or instantaneous? Because that's what happens in the real world. You know, some things turn on and off and on and off, or instantaneous. You know, you're designing the wing of an airplane, and you've got a plan for if lightning does hit that wing of the airplane, and there are differential equations involved and instantaneous driving functions. And so this is where the Laplace transform is going to be very powerful. Now in the first few sections of this, you're going to go, wow, we're in la la land, where are the differential equations? Because we're not really going to solve any differential equations in 10.1 or in 10.2. Let's define the Laplace transform. There was a mathematician named Laplace. He came up with this. Maybe later on we'll show you where did he come up with this definition, because this is really weird. You have a function that is defined on 0 to infinity, and that's usually going to be time. The Laplace transform of f is the function. So now look at this. It transforms it. We don't call it little f anymore. After it's transformed, it's called big F. And instead of the variable being t, the variable is s. And it is gotten by going integral from 0 to infinity e to the negative st f of t dt. And other notation for this is L of f. So f of s, L of f. And I know right now that seems a little confusing. Okay, that is the definition of the Laplace transform. What are we going to be doing in 10.1a? We're going to be computing some Laplace transforms. But before we do that, let's go ahead and show you this theorem here. This theorem which says the Laplace transform is a linear transformation. Wow. Okay, so what does that mean? You have the Laplace transform. It means that if you have r times f, r is a scalar, and then s is a scalar, s times g, f and g are functions, that you can do all those things that you wanted to do when you learned about functions. Go r times L of f plus s times L of g. Okay, so that's what it means. That's the linear transformation thing, and we're talking about vector space going to, vectors going to vectors, and here's linear algebra again. You can run from it, you can hide from it, but it's going to get you. So if you did not like linear algebra, ha ha ha, it's back. Find the Laplace transform. Okay, so there's three ways they can ask it in your homework. Find the Laplace transform written in words, or find L of f. Now we can kind of understand why they would say L of f, because that looks like f is a vector and it's going through a mapping, and L is the Laplace transform. And then f of s is kind of what you get over here. So here's f of t, and then f of s is over there. So you want to make sure you're comfortable with both of those notations. Let's go ahead and find our very first Laplace transform. And this is one of those days when I'm sad this is a video, because your first time doing a Laplace transform, you're just watching it on YouTube, when we really should have done this in class. Everybody's doing this for the first time. We could have brought cupcakes and, punch and all that stuff, but no, we couldn't do that thanks to the coronavirus. Let's go ahead and do this problem. Okay, the Laplace transform. L of f That's what we're computing. So what I'm going to do is I'm going to go ahead and write down that definition that we saw. This goes from 0 to infinity, e to the negative st, and then we have f of t dt. Okay, so what is this? This is the integral from 0 to infinity, e to the negative st, and then we have times our function f of t is t, dt. Okay, there's three things that probably disturb you about this integral here. One is it's an improper integral. Okay, and lots of teachers will say replace the infinity with a t. Well, we can't do that. Replace it with a w and put a limit. Yeah, that's cute. We're not going to do that. The second thing that probably bugs you is you're integrating with respect to t. So there is a constant. That s is a constant. So we can't forget that. And then probably the third thing that bugs people about this is to integrate this, we have to do an integration by parts. Now, I do integration by parts a lot differently than your average teacher. So I use this table method or the step method, which can get every integration by parts done. If you're interested in it, I'll try to put a few step method things at the end of the PDFs from 10.1a. So here it goes. Derivative, integral. I'm going to go ahead and put the t here. That's the one I'm going to take the derivative of. And then e to the negative st there, that's the one I'm going to integrate. So when you take the derivative of t, you end up getting 1. And you take the derivative of 1, you end up getting 0. Take the derivative of e to the negative st. Now, if it helps, you could actually kind of do this off to your side, e to the negative, like 6t. You would do a u substitution, or you can eyeball it, put a negative 6 out front. In any case, when you do this integration, you're going to get e to the negative st all over negative s. Now remember, s is a constant. We're going to integrate this again. So this is going to give us e to the negative st all over negative s times negative s, which is an s squared. And of course, we're kind of running off our table there. Okay, that's good. Now, I could go ahead and put the next one down, but I'm going to go ahead and multiply it by 0, so it doesn't matter. Who cares what goes there? The last thing I want to remember with this technique is to go plus, minus, plus. Now, why is that? Because our formula, when you integrate, you go uv minus integral v du. And so this is exactly the integration by parts, but this allows me to do this more efficiently. So what do we mean by more efficiently? Let's go ahead and do this. My answer then is going to be by multiplying these guys together. Whoops, I almost cut off that s there. And so when I do that, I end up getting, now don't forget that negative, negative t e to the negative st. I know that's like a subliminal message, test, watch out. Okay, so it looks like it says test. And then I'm going to go ahead and add this one right here, which is going to be negative e to the negative st all over s squared. Okay, so I'm not done with this because I still have to evaluate this from 0 to infinity. Okay, so there was the integration by parts. Okay, I'm going to rewrite this. So it says negative t all over, looks like I forgot something on this one. I forgot the negative s. So actually I got the negative, but I didn't put the s down there. So there it is. So this is going to be negative t, and then we have s e to the st power, cross the line, change the sign, and then this is, I'm going to do the same thing over here, minus 1 over s squared e to the st power. Okay, this gets evaluated from 0 to infinity. So the big question is, where are we going to be putting these limits of integration? What letter are we going to be putting those into? We are going to be putting them into t. Okay, so here is the deal. The first one I'm going to be putting into t happens to be an infinity. And so look what I have. I have like infinity over e to the s times infinity. So I'm going to have, like, it looks like negative infinity over infinity, which would be a L'Hopital's rule. Now this also is important, like figuring out if s is negative or positive. If s is positive, so let's say you have like a 6t on the bottom, you're going to have t on the top and e to the 6t on the bottom. You're going to have infinity over infinity, or negative infinity over infinity. But the heavy part is going to be on the bottom, and when you do a L'Hopital on that, you'll end up getting a negative 1 over infinity after you do derivative on the top, derivative on the bottom. So if s is positive, guess where this thing goes? This goes to 0, and that's where you want things to go when you put in infinity in there. So putting s greater than 0 will allow this to go to 0. So I've done a limit. I'm putting infinity in for t. I should really write it out as a limit, and that will be the case. It will go to 0 when s is greater than 0. If s is negative, then, you know, like if this is e to the negative 5t, then you can cross a line again, and it would be t times e to the 5t, or negative t. And then you would have like a negative infinity times infinity, which would mean it would diverge. Now, by the same rationale, if s is greater than 0, so think of this as like e to the 5t on the bottom, then you have 1 over infinity, which is also 0. So you got 0, you know, maybe a minus 0 over minus 0. That's the first part of the fundamental theorem of calculus, putting the infinity in for t. Now I'm going to go put 0 in for t, and when I do that, I'm going to get 0 for my first term, and putting 0 in for t on this one, I'm going to get minus 1 over s squared. So, wow, putting those limits of integration in, the infinity, we're always going to want to get 0, and that will happen when s is greater than 0. Putting 0 in for t, that zeroes out, and then this e to the 0 is 1, and that's why we're getting this. So this Laplace transform becomes 1 over s squared. We are done with problem number 1. That's our first Laplace transform, and that applies when s is greater than 0. So highly dramatic in the fact that there was an improper integral, there was an integration by parts, there was a constant s in there, but this is kind of how we carried this through. Now, if you're kind of wondering what just happened, we have vector t. We pushed him through the this linear transformation, and he became 1 over s squared. And this was for s greater than 0. And so there is our map. We'll come back and put the ones on here that we need to put on there. Let's go ahead and do the next problem. Okay, so I'll put the results from our last problem right on the top right corner there. Make sure everything is still clear. And now they're asking us to take the Laplace transform of 5t. So how do I take the Laplace transform of 5t? Well, L, I better just go back to black ink, of 5t. Now here's the deal, the Laplace transform is a linear transformation, so this 5 can come out front. So this is 5 times the Laplace transform of t. And didn't we just do the Laplace transform of t? It's 1 over s squared. So it looks like the answer to this is going to be 5 times 1 over s squared, which is 5 over s squared. S is greater than 0. And that is the answer. So when you already know 1 and you put a 5 in front of it, it's just going to be 5 times that Laplace transform. And so going back to this diagram here, we had a 5t, and I'll write that in green. This gets Laplace transformed to 5 over s squared. S is greater than 0. Okay, let's go ahead and do a few more of these problems, and this is basically what you do in 10.1a, and in the homework list I do break it up into 10.1a and 10.1b. All your 10.1a problems is using the definition of the Laplace transform to compute a Laplace transform. So let's go ahead and do our next problem here. F of t is equal to e to the 2t. So to take the instructions are find the Laplace transform. And the Laplace transform, I'm going back to the definition where it says 0 to infinity, and it always has this. It has e to the negative st times f of t, and this time I'm just going to write the f of t dt. Okay, so what does this thing equal? 0 to infinity, e to the, I can add those exponents, so this is just like if you had an x cubed times an x to the 4th, it's x to the 7th, so this is going to be 2t minus st dt. Okay, so this is the integral from 0 to infinity, just rewriting it many times, I guess. 2, no, that's not 2, that's a t, and then we have 2 minus s dt. Now, 2 minus s is just a constant. So I'm going to go ahead, you can do a u substitution and let u equal 2 minus s times t. I'm just going to go ahead and say, what is the derivative of that exponent? The derivative of constant times t is just the constant. We would like to have the constant sitting next to the dt. Let's just put it right here. 2 minus s is the constant. So I've got to put 1 out front, 1 over 2 minus s. To balance the books, I'm doing a u substitution here, but we call it the eyeball method. And so when that happens, and I integrate this, that's going to go away because this is the reverse chain rule, and we're going to have e, because the integral of e to something is e to something. So there's that something, and then this is all over 2 minus s. This gets evaluated from 0 to infinity. Okay, so now we didn't have to do any integration by parts. I know this u substitution for some of you was traumatic. So if you wanted to do the u substitution, you would say let u equal 2 minus s times t, and then you would say du, this is taking the derivative with respect to t, would be 2 minus s dt, and then maybe dt would be du over 2 minus s. And you can go ahead and do it that way if you want. You're going to get that. Okay, so let's go ahead and plug infinity in. What are we plugging infinity in for? We are plugging infinity in for t. So at first glance, this looks like it's going to be e to the infinity, which is infinity, over a constant, which is infinity. We don't want that to happen. But look at this. It's all going to depend on what 2 minus s is. If 2 minus s is a positive number, then this thing's going to diverge. It's going to be infinity. But if 2 minus s is negative, like so if this thing was negative, like negative 10, then it would get sucked to the bottom, and when you put infinity in for t, using limits of course, you would end up getting 0. So the way you can get 0 from putting infinity in is if, let's solve this, 2 is less than s, or s is greater than 2. So if we have that, when I go ahead and put infinity in, I will get 0. Now I'm going to go ahead and put 0 in for t. So remember, those are t values. And I'm going to get minus 1 over 2 minus s. There's the fundamental theorem of calculus. And so we can distribute the negative on the bottom. This is a stylistic thing. And we end up getting 1 over s minus 2. There's the Laplace transform of e to the 2t, and we'll note that s is greater than 2. Whew, so no integration by parts. We still had to do, an improper integral, and we still had s as a constant. But the more of these you do, the better you'll get at this. Here's something to ask, maybe. What if this was not a 2, but it was a 7? How would that change this? Well, you would have 1 over s minus 7. And if this was a 13, it would be 1 over s minus 13. And if this was a negative 2, this would be what? 1 over s plus 2. So in 10.1b, we're going to learn some shortcuts, just like we did with the derivative. This definition is kind of like the definition of the derivative with the difference quotient in the limit, and then after we derive some shortcuts, we'll see how to take Laplace transforms more efficiently and faster. So let's go ahead and put this on our list right here. We took the Laplace transform of e to the 2t. We ended up getting 1 over s minus 2, where s is greater than 2. Okay. Let's go ahead and do problem number 4, which might be our worst problem that we do in this section, just because of calculus skills. And this one's going to be quite dramatic. So this is the cosine of 2t. We are trying to take the Laplace transform of that, L of f. And this is going to be integral from 0 to infinity e to the negative st, and then we're going to put f of t there, which is cosine 2t dt. Okay, so that's what we have there. And how are we going to do this problem? Well, this is one of those integration by parts problems where you have a cosine and an e, and you could do the Linearity. So some of you have heard of Linearity, where this is log, inverse trig, algebraic, trig, and exponential. The exponential goes on the right, and the trig goes to the left of that. So when I do my stairs for integration by parts, I'm going to put the exponential right here, e to the negative st, and I'm going to put the cosine of 2t right there. Okay, so I'm going to go ahead and take the derivative of the cosine of 2t, which is negative 2 sine 2t, and I take the derivative of that. That's going to give me negative 4 cosine 2t. And look what's going to happen. This is not going to do what the other one did. What did the other one do? Well, this one zeroed out. We have 0 here. That was sweet. This one does not zero out. So some of you might go, oh, your stair method stinks, because what are you going to do? Well, let's go ahead and write some of these guys down. This is when you take the integral with respect to t, I get e to the negative st over negative s. This is kind of like, you could look at the other chart, that's exactly what I did last time. And then this is e to the negative st over s squared, and then this is e to the negative st over negative s cubed, and it keeps going. And you have to put a plus, minus, plus, minus, and alternates, because the integration by parts has a minus on there, and when you apply it twice, you'll end up getting a plus the next time. So here's the deal. When you do integration by parts, you're trying to integrate this thing right here. And that's what you see up there. So this integration by parts, I turn on the machine and it chugs along, multiplying these guys together, kind of like what it did right there. I was trying to integrate that, and then you get that and that. But what's going to happen on this one? I'm losing my pen caps. Is it's going to chug on forever. I'm going to get an infinite series, which I do not want to get. So it's all right to turn the machine on and let it chug away for a few steps. So it's, you know, maybe it's just like a gas-powered machine, and you're like, start it, vroom, 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 and it's like chugging along, and then you get this right here. I gotta circle that minus. And you can keep circling them, but at any time you can decide to turn off the machine. And when you turn off the machine, you have to write that product as an integral. Now, why would I want to turn off the machine there? Because that integral almost looks like my original integral. Okay, so my original integral I'm going to write as, I guess, I. And so I is going to equal, let's pick up the first two blue circles that I did. So when I do that, I have, and I don't even know if I'm going to have enough room to do this. Oh well, we'll just take our chances here. This is going to be e to the negative st cosine 2t all over s, and there's a negative in front of there. So that right there, I'll put a bracket there. That's from multiplying those together. Okay. Well, now the machine's going to keep chugging, and I'm going to multiply this. There's a negative here and a negative there, so that's going to be positive. I'm going to multiply that together for my next term. So I'm going to get plus 2. I'm rearranging things around a little. E to the negative st sine 2t. This is all over s squared. Okay. Now, because I've stepped the machine twice and it's chugging along, it's like, but, then I halt it, and I just go ahead and write that product, but within an integral sign. So look at this. I have two negatives there, so I'm multiplying that together, and when I multiply that together, I end up getting 4 cosine. Oh wait, I'm multiplying these guys together, so I'm sorry, I did this. I forgot that I was turning the machine off. There's only one negative, so it's going to be negative 4, and then it's going to be, this is all over s squared, and then I have e to the negative st cosine 2t, and I can't write it like that. Turning off the machine, I have to write it as the integral. Okay, so I think what I'm going to need is another piece of paper here. Now, I've just turned off the machine, and then also these guys have to be evaluated from 0 to infinity, and then this integral becomes 0 to infinity. Wow, so let's take a look at what I have here. This was my original integral right there, and I'm integrating e to the negative st cosine 2t, and look what I have right here. E to the negative st cosine 2t. So let's go ahead and write this. I call this integral I. I'm going to go like this. I equals. And we'll focus on one thing at a time here. So negative e to the negative st cosine 2t all over s plus 2e to the negative st sine 2t all over s squared. And then what I have here is this is just a constant with respect to t, and so we're going to go minus 4 over s squared, and then the rest of this just becomes my original problem, which I was classifying as I. So that's what I have there. So let's continue with this, and there is a 0 and an infinity there. So let's go ahead and put infinity in, and what do we learn when we put infinity in? We want this thing to be 0 when you plug infinity in for t. Now, if s is greater than 0, then it looks like e to the negative 7t, which then would get sucked to the bottom, and you'd have dne for the limit on there when you put infinity in, and then you would have, it'd be shooting to the stars there, would be over infinity. And so you would have the cosine, which would be like, I don't know where I'm going, but I'm in between -1 and 1, and then on the bottom you'd have e to the 7t, you know, or whatever s was that was positive, would be going to the stars, and that would dominate, and your limit when s is greater than 0, and maybe I should have written this lower, your limit would then be 0. And remember, s and s squared, those are just constants. And the same logic can be used here. If s is greater than 0, that gets sucked to the bottom. And it's going to be like e to the 10t on the bottom and sine 2t on the top. And you can see the e to the 10t would dominate. That's going toward the stars. And this guy doesn't, he's just going in between -1 and 1. And this whole thing will be going to 0. Okay, so there's putting infinity in. And now we're going to put 0 in for what letter? We're going to put 0 in for t. And you put 0 in there, you get a -1. You put 0 in for the cosine. Cosine of 0 is 1. And then on the bottom you have s. You put 0 in for t here, you got the sine of 0, which is 0. And so we have plus 0 right there. And let's not forget minus 4i over s squared. Okay, so bottom line is when you put infinity in, and on the problems we're doing, you always want the integral to converge. You don't want the integral to go to infinity. Let me fix this up now. I'll forget to fix it up if I don't do this. Okay, that looks a little better. And so let's go ahead and bring this thing that has an I, we'll bring it to the left-hand side. So I have I plus 4i over s squared. This equals, and on the right-hand side, I'm going to have, all this thing becomes is 1 over s. Now I'm solving for I, which was my original integral. I'm going to multiply both sides by s squared. So I have I s squared plus 4i equals s. I'm going to factor out an I. So I have s squared plus 4. This equals s. And I'm going to divide both sides by s squared plus 4. When I do that, I end up getting my integral, or the Laplace transform, is s over s squared plus 4. And this holds true when s is greater than 0. So we've completed one of the harder problems here in the homework, or in the notes. And in the homework, I think you're going to get like a sine of bt. You can replace the b with an 8 if you want, and try doing it that way when you do your homework. But look at this. We had our original function was the cosine t, cosine 2t, and the Laplace transform was s over s squared plus 4. So what if it had said the cosine of 3t? What do you think the Laplace transform would have been? Well, s over s squared plus, if there's a 3 there, 9. And so, I mean, we're kind of hinting that there are shortcuts. I'm going to go back to my diagram here. And in red ink, I'm going to put the cosine of 2t. And I'm at 34 minutes. What do we have? Our Laplace transform is s over s squared plus 4. S is greater than 0. So you can figure out what's going to happen when there's a sign there. Is it going to look similar, or is there going to be a little difference? Well, when you do your homework, you're going to find out what happens. Okay, so we have one more problem to do, and before we do that problem, I want to let you know that well, for one thing, Laplace transforms, we've been going this way to this way. We're going to learn some shortcuts in 10.1b, and then in the next section, we're going to learn how to go back. And when we go back, we'll be using shortcuts to go back. So let's go ahead and show you this note here. You can take the Laplace transform on piecewise continuous functions on 0 to infinity. Now, piecewise continuous, what does that mean? Because I have not defined that. That means if there are discontinuities, they are either removable or jump, but never infinite. And in the real world, there's a lot of real world problems where the driving function is piecewise continuous. So let's go ahead and do our last problem. We are going to find the Laplace transform of this piecewise defined function, which happens to be piecewise continuous in the sense that the discontinuity there, I think, is a jump discontinuity. So let's go ahead and do this. How do I find the Laplace transform? Well, L of f, it almost seems like it would be very hard to write, so let's just write out this. 0 to infinity, e to the negative st, f of t, dt. Okay, so you're like, okay, Joe, you just wrote out the definition. That's right, because I'm panicking. I don't know what to do. So what I'm going to do is I know what this function is from 0 to 3. It is 2. So I could put a 2 there. And then I know what the function is from 3 to infinity. It's a 5. So I'm going to break this integral up into 2 integrals, the sum of 2 integrals. And so this is going to go from 0 to 3, and then I'm going to go f of t will then be 2. So I'll write it like this, just so in case you're wondering what happened. And then the other part's going to go from 3 to infinity, and there's not an equal sign there. I just panicked or whatever. I just went really quickly. Be a plus sign there. And this is going to be e to the negative st, and then we're going to put the function. So if it's at 5t there, we'd put a 5t there, but I'm just going to put a 5 here. dt. Okay, so now I have to integrate. Now I have to do 2 integrals, 2 improper integrals. Remembering that s is a constant, and let's see if we can do this. The integral of e to the negative st. Well, you need a negative s out front, so I put one there, and then I divide. I'm eyeballing this, by the way. And what this thing gives me for the integral is 2e to the negative st all over negative s. So that is the integral of this right here. If you want to do a u substitution, you could say u equals negative st, and that's kind of did the u substitution in my head. And so this gets evaluated from 0 to 3. Actually, it's not 2 improper integrals. It's just a regular definite integral there and an improper over here. Now, by the same logic or the same integral techniques, I'm going to go ahead and write out this one. It's going to be 5e to the negative st over negative s. And this gets evaluated from 3 to infinity. Okay, now I'm going to go ahead and put these values in for t. So I'm going to put 3 in for t, and I'm going to get 2e to the negative 3s all over minus s, or negative s, and then I'm going to put a 0 in for t. This is going to give me, okay, so minus 0 in for t, it's going to be 2 over negative s. Okay, so I'm done with that. Now I'm going to go ahead and put infinity in for t. Now, in order to do this, for me to get 0, I need the s to be, and maybe you can take a guess, greater than 0, because if s is greater than 0, then this would be like e to the negative 100t, which gets sucked to the bottom, and that's what we want. So we would have a 0 there. And then I'm going to go ahead and put 3 in for t, so I have the fundamental theorem of calculus, as I put that there. We have 5e to the negative 3s. This is all over negative s. Okay, now I just have to clean up this answer. And actually, these two creatures right here, and this one's actually a positive 5, they're the same creature. So I have 5 of those creatures here, and minus 2 of those creatures there. Those are like terms. So that's going to give me 3 of these creatures. And then over here I'm going to have plus 2 over S. Now I kind of messed up here. So what I messed up on is I just kind of jumped the gun. I have 5 of them here and negative 2 of them there, so that negative doesn't go. There we go. Ooh, did this left-handed. Wow, I've got skills. I am marketable. Okay, so here is the answer. That's the Laplace transform of this piecewise continuous function. Now, some of you would choose to write your Laplace transform as 3e to the negative 3s plus 2 all over s. And some of you would have chosen to maybe bring that e to the negative 3s down below and make it e to the 3s on the bottom. That's cute, it works, and in fact it was encouraged when you first took algebra. But when we start solving differential equations that have this as a driving function, you're probably going to want to keep your e's with negative exponents. It's just going to help you skip a few steps when you do that. So I think we have enough on here. What I'll do after this is you could pretty much, do we have this? For most of you, turn off the video. But for those of you who want to know how did they think of the Laplace transform, I'm going to go ahead and edit the video so I put a little PowerPoint right after what I'm about to do. So for those of you who don't want to sit through the how did they come up with the Laplace transform, you can turn the video off and have a good day. How did they think of the Laplace transform? Now, when I say how did Laplace come up with the Laplace transform? So we're going to kind of go over the motivation for that. And really, you don't have to know this for your homework. So how did they think of the Laplace transform? Well, it was kind of motivated from the power series. The power series, you might have remembered this from second semester calculus. It's n equals 0 to infinity, a sub n x to the n, which equals a to the x. Okay, so this gives you, we had the infinite power series. And here's the cool part. If a n equals 1, so you can think about this, go back to, thinking about calculus second semester. A of x, what does that equal? Well, that's just going to be a1 plus x squared. Looks like geometric. Happens to be the 1 over 1 minus x. There's the geometric series. And that converges between negative 1 and 1. Now, if an equals 1 over n factorial, an is a sequence. Now, in calculus 2, it probably wasn't presented this way, but I'm doing this on purpose. Then if you had a factorial on the bottom, and some of you would remember what a of x, because, what it is, that converges to e to the x, and that converges for all x. It's not just between negative 1 and 1 on this one. So there is a continuous analog, and it happens in probability too. Like when you first learn probability, you roll a die and you say, what's the probability of 5 comes up, and it's 1 over 6. That is the chunky probability, like chunky peanut butter. And then if you keep taking probability, you end up getting something like, what is the probability the light bulb burns out after 50 hours? And now you can't just place all your outcomes in a box, and that is the continuous peanut butter probability. Well, this is what we're doing. Here's chunky right here with you're doing a summation over some integers, and now here's the continuous analog. The continuous analog of the summation is the stretchy s, the integral. And so integral from 0 to infinity, we keep, instead of saying an, we say a of t, and then we have x to the t dt. There is a of x. So this is what Laplace maybe was thinking about. Now, because we like base e, we are going to change this right here, this x to the t. We're going to change it e raised to the ln x. That can go pop, and that's really just an x, so x to the t. And what then we'll do is we want our integral to converge. So remember, the ln of x, when x is between 0 and 1, that ln x will be a negative number. Think about the graph of y equals ln x, and that will suck that down to the bottom, making the integral converge, making ln some negative number. And so what we're going to do is we're going to replace the ln x with a negative s for some positive number s, because we just said that ln x is, we want that to be negative, and or it is. And then we're going to change a of t to f of t. And so this integral right here is going to become this guy right here. So a of t is f of t, and then we have e to the negative st dt. This is f of s, which is the Laplace transform, and that's what we've been doing now with the Laplace transform. Lots of times we'll say that t is time, and I've said that before, and s is going to be frequency. So that is probably the best explanation that I could give. A transform actually changes variables. So when you do Laplace transform, you go from the world of t to the world of s. An operator now, which is different than a transform, does not change variables. So when we had those derivative operators like d squared or d, we did not change variables. Well, that is how did they think of the Laplace transforms. You guys have a good day.